Good afternoon, everyone. Welcome to the Design of Reinforced Concrete Structures Week 8. Today's session is scheduled from 3 to 4 p.m. It will be a problem-solving session for the design of columns. As you had already gone through the lectures given in week 8, it was for the design of columns for short columns under compression with uniaxial bending and biaxial bending. Today we will be doing a problem related to the analysis of column which is having uniaxial bending. That is the axial load is coming on a column with some uniaxial eccentricity. So let me start first. I will give you a brief concepts about what we mean by the uniaxial bending of columns. Later we will solve a analysis problem on that. We will try to find the capacity of a column under uniaxial bending. Hope my screen is visible to you. So let me start. So in the last lecture, we go to the last one. In the last lecture, I told you about that there can be the types of columns depending upon the eccentricity of the loading. For example, if it is along the centroid of the column, then we will treat it as an axial loading. But if the load is not acting along the centroid of the column section, but it is having some eccentricity either with respect to one axis or the both axes, then we will have to consider the moments that will be coming due to this eccentricity. There can be the moments in only one direction. We can treat it as a uniaxial eccentricity, and the coming moment will be uniaxial only. And we can treat it as a biaxial moment also. Here the eccentricity is with respect to x-axis as well as y-axis, major axis and minor axis both respectively. So we have to first analyze this column and come out with its strength, and then we have to design it according to that. So there can be uniaxial, uniaxial bending, uniaxial bending. Uniaxial bending is like this. For example, if we have a column section like this, it is having one major axis like this, one axis like this, another axis like this. There are two axes. We will have xx, yy. For example, this load is not acting along the centroid, but it's acting somewhere here, like this. With respect to y, it's having zero eccentricity, but with respect to x, it's having some eccentricity. Means that it will be due to this. For example, if the load is it's the top side of the top wave of the column. For example, if I draw the side wave of the column like this, if it's this is the axis, the load will not be acting like here. It will be like acting somewhere here with some uniaxial eccentricity E. Due to this eccentricity, for example, if this is P, there will be some moments coming on this P moment. So we have to incorporate this P moment also in our analysis problems, as well as later on when we try to design this column section as well. So for example, this is the column section. It's having a reinforcement like this on the all four sides. It's reinforced, and it's the stirrup. Let D be the major dimension and B be the minor dimension, and D dash is a cover provided, clear cover provided. So, for example, it's acted upon by some uniaxial moment like M, like this, uniaxial moment like this. So it's having some uniaxial eccentricity. We will try to draw its strain profile. Strain profile will be like this. For example, this moment is acting on this column section like this clockwise. So if we draw this section, this moment will try to bend it like this. So we can clearly see from this, this part of the this part will be in compression and this part will be in tension, like this. There, here it will be in tension and here it will be in compression in this side. So we will have to now not only to calculate the compressive capacity of the column, but we have to take the tension side as well. For example, this moment is acting here like this, then this part of the column will be under compression and this will be under tension. So if I take this compression side, here it's crossing this much amount of column will be in compression, this much amount. Outer side as well, and this will be in tension, this much amount. This much amount of the section will be in tension because you can relate it from the strain profile here, from the strain profile, because sorry, you can relate here strain profile like this. Here it will be in negative, will represent with negative, and here it will be positive compression, and this will be tension. So our strain profile will be like this. This will be the neutral axis for it. Neutral axis. So now we have to find the strain at each reinforcement, and then we have to find the new compressive force, total compressive force acting on it, total moment coming on it. For that, the code gives the formula like this. This can be easily derived from the integration, but we will not go into the detailed calculation. We only require the formulas for solving our analysis problem. So let me draw the stress profile for this as well. Stress profile will be like this. If this is starting from this point, stress profile will be like this. It will be from this side, it will be 4.447 FCK, because we all know these assumptions from the flexure. Same assumptions will be applied here. That is, in flexure, we take the maximum compressive strain in concrete as 0.0035. Same assumption is applied here as well. We have to take the maximum strain in concrete at the most compressive strain fiber as 0.0035. Same here applies. So the stress block will be also like the same way. It will be straight rectangular for sub part, and there it will have a parabolic variation like this. It will have parabolic variation up to our neutral axis depth, because after that we have to ignore the concrete which is in tension. These are the basic assumptions of the flexure. So we will write here it's 0.447 FCK. FCK is the characteristic compressive strength of concrete. So our total resultant compressive force will be acting somewhere here. Is this correct? Somewhere CC, and it will be acting at some X bar distance from the most compressive fiber, most compressed edge. And our, if we will see on our these, this with small colors. So in the part where the concrete is in compression, the steel bars or the rebars will be also taking the compressive load. So we will show the force in the rebars like this, compressive force in those, but it will be in the decreasing order because the compression is decreasing towards the neutral axis. So it will be in decreasing order like this, and it will be it will be minimum and zero here. And the rest of the bars that are in tension zone, they will be taking up the tension. We will show like it like this. Here it will be somewhere here, and here it will be maximum tension at the outermost reinforcement line. So we have to first we have to calculate the strain in each rebar line for compressive part and the tension part as well. Here it will be XU, it will be our XU, depth of the neutral axis. XU will be here, and from the in centroid we denote this as YI. And for example, we take this side as positive and this side as negative. For example, we have some reinforcement line here from the positive side of the this centroidal axis. For that, we take y as positive, and for those which lie on the negative side of the centroidal axis, we take that as negative. Here, this is the centroidal axis. Centroidal axis. So this was the case for when our neutral axis was lying inside our column section. That was x was less than the less or equal to d. If this neutral axis lies outside the cross section of our columns, we have to do differently, because there the neutral axis, we have to extend our strain profile there. I will show that as well. So if this was our column section, same column section, sorry. Same column section. For example, now the eccentricity is too large that the whole column section is like this one. I will draw first this reinforcements. For example, I am just denoting it by lines, the reinforcement that is provided inside the column section. Like this, like this. There will be third reinforcement line, this, like this. 1, 2, 3, and 3 also on the other side. 1, 2, and third one like this. I'm not drawing these symmetric, but these are symmetric. Let for time being, we'll take these like this. This is the centroidal axis of our column section. This one, huh? This one is the centroidal axis. Let's do it like this one. This is the centroidal axis. So I am saying that for this case, our neutral axis was like somewhere inside the column section. Moment was not that much high that it was taking the neutral axis to go beyond the section. But if in such cases the moment is acting on our uniaxial moment acting on our column section is that much high that it makes the whole column section to go under compression, such that the neutral axis shifts beyond the column section. It will be, in that case, it will be like this. I'm saying that the whole strain profile, that the strain profile of my column section like this, from this to the full section is under compression, because the moment this time is too that much high, like this. I assume that you all are aware with these assumptions, that why I'm doing making this line linear and then this one, because in the flexure you already studied that along the depth we take the strain variation as linear. So I assume that all these concepts you are well aware with these concepts. Look at this strain profile here. You can see that the whole column section is compression. So if I take this, extend this profile like this, with another color. If I extend this profile like this, I will have somewhere where this compression strain becomes 0. So there will be the point where I will have my neutral axis. If I draw a line along this point, you can clearly see this is the neutral axis. So my neutral axis depth now becomes, first I will write, this is the neutral axis here. So this all along from the compression side to this one. Now this becomes the neutral axis depth, XU. Okay, this becomes the neutral axis depth. And whole column will be in compression, so the stress block will look like this, the one shown here. Stress block will be like this. So whole stress block is in compression. It will be 4.447 FCK. It will be like this, like this. It will have some like this. It will be the here. It will be 0.447 FTK, and our resultant compressive force will be acting somewhere here. No, it will be like somewhere little bit for the other side, no, like this. So the resultant compressive force CC will be here due to the concrete section. It will have some distance from the most compressed fiber like this X bar. And one more thing, these all bars will be these are actually rebars. One rebar is provided here, one is provided here, maybe on the side there will be another one here, and here it is one from this side, another from this side. All these rebars will be subjected to compressive loads only. So they will be taking the compression only like this in the decreasing order. Because the compression is max here, minimum here, this neutral axis. Yeah. So it will be like this. It will little bit increase, next line little bit increase, and then after going on increasing. I am denoting the compression taken by the ith line of the rebars as CSI. And here the index I already told you, you have to take, if it is yi for yi line, this distance yi is positive if it is on positive side of the centroidal axis, and negative on the negative side of the neutral axis. Positive side, negative side. CSI ith line compression force taken by the ith line rebars. And similarly, this will be the strain epsilon SI in the ith line. Epsilon SI. Same will be the case here. I forgot to write here. Same would have been here, like this epsilon SI. Epsilon SI. This was the case for XU less or equal to D. The case that I draw here is XU greater than D. Neutral axis lies outside the column section. So this for CC as a formula as per code given as, the CC is given as compressive force taken by the concrete as A, FCK, B, and D. B is the minor dimension, D is the major dimension. I have shown it here. This B and this D. Okay. And A is a stress block area factor. stress block area factor is like this. This stress block, for example, when we have to take this compressive force taken by the concrete, we have to integrate this area. You remember it from the flexure that for flexure this A factor comes out to be 0.362 FCK but here it will be the different case because here our neutral axis may lie inside the column or outside the column section. So depending upon that factor, our A also varies. A. As per that, our A varies like this. A is equal to 0.362 XU divided by D. If XU less or equal to D, that is the neutral axis lies within the column, or it is given as 0.4471 minus 4G by 21 if XU is greater than D. Okay, there is another one factor G. The G is given as, these all formulas are given in code. 16 divided by 7XU by D. 7XU by D minus 3 4 whole square. Okay, and then corresponding moment MC carried by the concrete section, which is under compression, as it will be. Let me show you. This is CC force. Okay, this is X bar. It's acting at some distance. This is CC force. It is acting some X bar distance from the most compressed fiber edge. So it is distance from the centroidal axis will be, it is d by 2 here. Clear? D by 2. This distance will be d by 2 minus X bar. So if I have to write the moment about the centroidal axis for this for CC, I will write MC as CC times lever arm. Lever arm is here d by 2 minus X bar. D by 2 minus X bar. Same, I will write the formula for MC here as CC times d by 2 minus X bar. Okay, and for this X bar also depends whether the neutral axis lies within the column or it's outside the column section. So accordingly, our X bar expression for the X bar modifies like this. If it is within the column, it is same as flexure X bar 0.416. Everyone remembers this. It's 0.416 XU in the flexure. And if it is outside, that is XU less or equal to D. And if it is outside, it will be given as 0.5 minus 8G by 49 D divided by 1 minus 4G by 21 for XU greater than D. You don't have to worry about these formulas. These all are given in code. You can see it from there. Okay, for this. Now, this is the compressive force carried by the concrete. This is the moment resisted by the concrete. So next will be on the rebars. What is the amount of compressive force carried by the rebars? So CC, CS, the resultant compressive force in this steel will be, CS will be summation. We will write it in like this: I running from 1 to N FSI minus FCI ASI. I will tell you about all these terms. ASI is, for example, we are taking this as ith line of the reinforcement I. So the area here will be, this is denoted as ASI. For example, we have one rebar here, we have another rebar here. It has area bar AB. Here it is area bar AB as well. ASI will be equal to 2AB. That is the area of the steel bars in the ith line. Okay, that is ASI. Same FSI. Same FISI is the stress in the rebars at height line, FSI. Okay, design stress in the ith row. And same FCI is the design compressive stress level in concrete. For example, if this rebar is in compression here, the surrounding steel, concrete will be also in here in compression. So FCI is the design compressive stress level in concrete at the ith row. You have to remember these things. FCI, FSI, and MSI moment and resisted by the steel MS will be similarly equal to same compressive force multiplied by lever arm. I running from 1 to n. Uh, FSI minus FCI into ASI. I'm writing the same ASI, and you will see from the centroidal axis. I already wrote it is as YI. The distance of the each bar, and we are summing it over all the lines of reinforcement bars, we will get the total moment as yi. So these are all the formulas that we have to remember for analysis part of the short columns under uniaxial bending. And here we can have this FCI design compressive stress level in concrete, and I throw as FCI will also depends upon what will be the strain in the steel at that part. If the strain in the steel is zero, the stress in the concrete is zero. Normally, epsilon SI less or equal to zero. If it is epsilon SI is greater than or equal to 0.002, it is given as 0.447 FCK. If it is below 0.002 or otherwise, it is given by a formula 0.447 FCK. 2 into epsilon SI divided by 0.002 minus epsilon SI divided by 0.002 or whole square. Otherwise, okay. These are the formulas you have to remember for solving a problem. So let's solve a problem on this what we have studied. We have problem number 8 for the week 8th. So once more, you would have studied in the lecture that similar to the sections we would have in this flexure, we were having under reinforced section, over reinforced section, and balance section. Same in this columns, analysis of columns, we are having those same similar three sections. Balance section where simultaneously the maximum strain in the most strained concrete fiber reaches simultaneously with the steel. Steel also reaches the yield strain, and the concrete also reaches the strain of 0.0035. That is the balanced section, and the failure at that section will be called as balanced failure. Uh, at that time, the eccentricity of the loading that is acting on our column section is said to be balanced eccentricity EB. So everything is related with this eccentricity EB. Balanced section. For balanced section, it is denoted as EB. For example, if EB is now the eccentricity on our column E is such that it is less than balanced eccentricity, then for our column we will have only compression failure. For example, if the load is acting on our column, it will be only subjected to full column section will be subjected to compression, and the column will fail only under compression. Then there will be, if this eccentricity is high enough, E is greater than EB. EB is with this eccentricity, for example, it was having first E. Now this load is acting somewhere here. It is very much large. E is greater than EB. Then this P will create such a high moment that it will bend the column like this. This side will be in compression and this side will be in tension. The tension will be so much high here from this side that the concrete will ultimately fail in tension. That is the tension failure. Tension failure, compression failure, and this is the balanced failure. Balanced failure. So in our problem, we are giving a section where there is occurring a balanced failure. That's E is equal to EB. We are having a column section like this. Column section like this. It's having um, rebars like this. It's one rebar having like here, another rebar here, another one here, and one here, and one at the centroidal axis. Yes. One, two, three, four, five, six, seven. We have another here at the centroid here. This is the reinforcement given to our column section. It's having stir up like this. It's having stir up like this. Okay. The dimensions of the column are major dimension is, I will write everything in mm. Major dimension is 500. Minor dimension is 300. Analysis problems for columns are usually very lengthy. These are 8 diameter ties, and this is main rebars are, these are 6 bars. 1, 2, 3, 4, 5, 5, 6, 6 rebars, and all are 25 diameter. Okay, 25 5. And concrete will be used in this is M25 that has been used, and steel is Fe415 grade. Okay, and this is the column section. So we will draw the, for calculation parts, we will draw the section like this. Okay, calculation parts we will draw for the simplicity. Okay, this is our section, and for simplicity we have to draw these reinforcements like this. This one, for this is one reinforcement line, this is second reinforcement line, this is third reinforcement line. Okay, we have all three reinforcement rows. Okay, our load, it will be having it will be having load capacity pu, pu corresponding to the balanced section pub. Okay, and it will be having moment carrying capacity mub corresponding to balanced section mub. And I'm writing the subscript x as well because the bending is only along x-axis, pubx and mubx. Okay, so if I do all the calculations regarding this 25 5 bars and 8 5 ties, and my section side is 500. So when I calculate all these things, I will get a, this effective cover. This, remember, effective cover is from the centroid of the steel bar. Okay, clear cover is from the, I get an effective cover of 60.5 mm. Why I'm calculating the effective cover? Because I need this in the strain profile to calculate the strains in each row. So I told this, I will write this as centroidal. I will take this as centroidal part. Okay, I will take this as centroidal part. So with respect to this line, all the calculations will be done. So I will number it. Okay, this is yi. I'm taking this as yi. Okay, I will take this as I equals 1, I equals 2, I equals 3. Okay, I equals 1, I equals 2, I equals 3. And same on this, it is 60.5 mm from this side. This will be 60.5 mm from this side as well. Congested, lot more congested there. We'll write here it from the centroid. This dimension is 60.5 mm. Okay, let me write it here as it's a highly compressed edge. Okay, highly compressed edge is this one. So for this column section, we will draw the strain profile. Strain profile will be like this. Okay. We will have to close somewhere here. Okay. Strain profile like this. Okay, we will have this will be in tension. This side, this will be in compression positive side. Okay. Epsilon Cu. Here it will be 0.0035 strain the highly compressed fiber. Okay. Here it will be, so the strain corresponding strains here to these sections. This will be 1. Okay. This will be another one. Here the neutral axis is this point. Remember, neutral axis is this point and centroidal axis is this. So our neutral axis is not passing through the central axis. I will show you right now. I will show you because this is the centroidal axis. If you remember, centroidal axis is d by 2 distance. Okay, d by 2 distance is about 250 mm. Okay, and when we will calculate this neutral axis, it will not be 250 mm. So here it will be our neutral axis depth xu. Okay, xu. Here this small will be epsilon s2. And second row, strain in the second row of the steel, strain in the first row of steel, and strain in the third row of steel. Epsilon this is epsilon S3. Okay, strain and the corresponding stress block. So let me draw the corresponding stress block quickly. Corresponding stress block will be like this. Like this. Neutral axis is this point, so we will have joining from this point. It will be 0.447, a rectangular for some part, and after that it will be parabolic up to this point. So this will be our 0.447 FCK. This will be our compression force acting somewhere. Let me show you, as I already told, as you can see that neutral axis is lying within the column section. So our x bar distance will be from the previous formulas as 0.416 xu. Okay, look at here. 0.416 xu for xu less than d. Okay, 0.416 xu. This is cc, compression concrete, and this will be the respective compression forces in. This will be in steel row CS3, and this will be in. I'm showing it here because these will be in CS2 and CS1. Okay, forces in here. These will be in tension. This will be in compression. Okay. See, this is, we calculator showed all the quantities. Now we have the calculation part. If you are able to draw these diagrams carefully, your analysis part will be very easy because everything will be calculated from here. Everything, similar triangles will give you everything from here. So for we have uh, this is AS1, AS2, AS3. You can see that every row is having same number of bars. So AS1, AS2, AS3 will be equal. AS1, AS2, AS3, AS3. These are 25 bars. These will be 2 into pi by 4 d square. 2 is the number of bars, pi by 4 d square is 25 square. Okay, it is 982 square. Okay, so y1, that is why I already told you that from the negative side of the new centroidal axis it will be negative. Y1 will be minus this y1. Okay, this y1, this distance, this will be y1. Okay, this will be y1, this will be y3. Clearly see these things. This will be y3, and you can clearly see y2 will be 0 because y2 I2 row is along the centroidal axis, so y2 will be 0. Y1, if you have to calculate, you can clearly calculate it as y1 is equal to d by 2 minus effective cover 60.5. That's why I told you calculate it carefully as 60.5, precisely d by 2 minus 60.5. Y1 is equal to, it is total minus, first is the sign convention minus, so it is d by 2 minus 60.5. This comes out to be 189.5 okay. Y2 is 0. I told you why y2 is 0. Y3 is positive and it is the same distance, d by 2 minus 60.5 It is 189.5 This is negative, this is positive. Okay, so neutral axis depth, this was first calculation, this was first calculation, this is second calculation. Neutral axis depth. Okay, neutral axis depth. For neutral axis depth, first we will see the since I already told you that this is a balanced section. So simultaneously a strain of 0.0035 will be achieved in the highly compressed concrete fiber, and yield strain will be achieved in the highly tensile reinforcement fiber. So yield strain for yield strain or epsilon y for Fe415 is 0.87 Fy divided by Ey plus 0.002. These formulas are all from Flugjet. That is 0.87. We have used Fe415 steel 415 divided by Young's modulus is 2 into 10 power 5. These all units are consistent. You can check 0.002. Okay. You will get a value of 0.03805 as the yield strain in steel. Okay, epsilon y. So this one, this is the yield strain in steel. So if I have the similar triangles, I have strain in steel here like this, I have strain in concrete like this. These are joining like this. Okay, I have like this, sorry, I have like this. Okay, this is greater, this is 0.0038, this is 0.0035 as per the definition of a balanced section, and this is given as depth of the neutral axis xu, and this will be given as, this is obviously this is y1. Okay, so I have to calculate xu. So from the similar triangles you can clearly calculate the xu as, xu will be equal to 0.0035 times 500 minus 60.5 Divided by 0.0035 plus 0.0038. This comes out to be XU, neutral axis depth, comes out to be 210.6 mm. And our d by 2 depth, that is the neutral centroidal axis depth, is 250. Clearly you can see that neutral axis depth is less than the centroidal axis depth. That's why I showed that here. This is the centroidal axis CA, and this is the neutral axis. This is the neutral axis, because neutral axis depth is coming only as 210. This is coming as 210, and but this whole depth, this d by 2 is 250. That's why in the figure I showed it some slightly away from the centroidal axis. This is centroidal axis. Okay. So we got the depth of balanced depth. It's in fact balanced. Okay, because the section is balanced. X to B. So we got the balanced depth of the neutral axis. Now we have to calculate the strains. We have to calculate the strain in steel. Strain in steel. We have three steel rows. We have three steel rods: epsilon S1, epsilon S2, epsilon S3. I already told you beginning tension is negative and compression is positive. Tensile strains are negative and compressive strains are positive. So epsilon S1 is a tensile strain, it will be negative. Okay, minus epsilon Y. Why is it epsilon Y? Because it is the outermost steel fiber and it is balanced section, so it will have completely yielded. So we are taking the yield strain epsilon Y as minus time is 0.0038. Okay. 3805. This is tensile. Okay, this is tensile. Epsilon S2. That is as the second row. This will be minus times. From the similar triangles, you have to calculate all these quantities, because look, I have this value. I have these distances. I have these distances. So all the distances are calculated like this one. I have this value 0.0038. Then I take a triangle like this. I come up to this point where the neutral axis depth is this one, and after that, this is this one. This is d by 2 minus. This is d by, sorry. Actually, this distance is this up to this. This is xu. Okay. Let me show it from here only. For epsilon 2, you have to calculate epsilon 2 here. Epsilon 2, you have to calculate. So from this, we will take this one. We have calculated this distance. We are already calculated. We have this whole distance. We have this 60.5 distance as well. So we can easily calculate this epsilon S2. So this epsilon S2 we can calculate like this as 0.0035 multiplied by 250. That's d by 2 minus 210.6. 210.6 divided by 210.6. 210.6. Okay, this is small, this one, this is this one. Okay, this is similar triangles like this. Okay, this is 0.0035. This is XU. Okay, this is at the centroid 250. 250. This is XU 210.6. This is epsilon S2. Okay, calculate this distance. This will be 250 minus 210.6. Apply the similar triangles. This triangle, this triangle. Similar triangles row epsilon S2 divided by 0.0035. will be this corresponding side 250 minus 210.6. This side 210.6. Look, I have written the same expression here. Okay, epsilon S2 is equal to 0.0035 into 250 minus 210.6 divided by 210.6. Negative sign is because it's tensile strain, okay? Or already told you. Similarly, you have to calculate the epsilon S3. Epsilon S3 is the compressive strain. Epsilon S3 will be equal to similar triangle, same theory you have to apply for the similar triangle. It will be plus 0.0035 times, it will be 210.6 minus 60.5. 60.5 is the clear cover. If you draw the similar triangle for this as well, you will get this one, 210.6. It is 0.00249. Now this 0.00249 is compressive and it is also greater than 0.002. I will tell you where we will require it later, 0.002. Okay. So design stresses in steel. Now we got this strain, these strains in steel rows. So corresponding design stresses will be calculated. These design stresses you have to calculate in steel row 1. FSN will be the design stress as 0.87 Fy. 0.87 Fy because it has yielded. Okay, I already told you. It will be minus 360.9 megapascal. Negative because it's tensile. Okay. FS2. FS2. We can see that FS2 here. We have calculated FS2. It will be. It came out to be minus 0.00. It's less than 65. Okay. It is less than 0.002. It means that it has not yielded. So we directly apply the formula of stress is equal to straight Young's modulus. Okay. It will be 2 into 10 power 5 multiplied by 0.0065. This comes out to be 131 MP. Okay, MPa. FS3 will be like this one. Now here it is greater than 0.002. So you will have to calculate it. FS3 as you will get, if you calculate it in a similar manner, you will get 345 megapascal MPa. I showed you in the some lectures that I have a table for this one. You can find it from the next values. I have a table for this stresses. Wait. Yeah, I have a table for this. Actually, yeah, this table. Okay, Fe415. You can get these values. You have corresponding strain here. Whatever strain there will be, you interpolate and get the value here. Okay, from there I have got all these values. I have got this 345 megapascal. Okay, so now we have to calculate the design strength. So this fourth point, we are finishing it right now. Design strength component. Design strength component in axial compression. Compression PUX that I already wrote. Okay, and it is balanced as well. PUBX. PUBX. This will be the contribution both from concrete, CC, and from steel as well, CS. Okay, CC. I have a formula. CC is equal AFCK BD. Since our neutral axis is less than the major dimension D, or it lies within the section, so our A will be 0.362. Okay, I wrote it already. It will be 0.362. Okay, A will be 362. Okay. FCK and FTK XUB. Actually, A is this. A is 0.362 x u by d. Okay, it is BD. It is B into D. So we will write is 0.362 x u balanced by d. Okay, this is for A. We substituted it for A equal to A. We have F, C, K. We have B. We have D. D cancels. Okay, we got this expression. So we substitute the value of FCK as 25 and B as 300. And XU balanced as 210.6. We will get the value as 57,177.9 newtons. Okay, this is the contribution from the concrete. Contribution from the steel CS will be the formula. We have to apply summation I running from 1 to 3. These are 3 rows of steel CSI from the individual CSI. And CSI is given as, this will be summation FSI minus FCI. All the formulas that I wrote earlier. ASI. Okay. So we have to take the summation I running from 1 to 3. We have to take all the summations. So we have FSI in for I running for I equal to 1, that is the first row. It is minus 360.9. We will write directly minus 360.9. Okay. Then FCI, we are not writing FCI here minus FCI because FCI is 0. FCI for ESI less or equals 0. Okay. Minus 360.9, it is minus 131. That is the second. And third, here we have the problem. 345. I wrote 345. Okay. FS3 is 345. But ES3, you can see here, ES3 is greater than 0.002. And here from this formula, you can see that for ESI greater than 0.002, we have to subtract 0.447 FCK. Okay. Minus 0.447 FCK is 25, and ASI for every row I already calculated, these are equal and it is equal to 982. So when I calculate PUB comes out to be this comes out to be minus 15 to 30 this Newton. This is tensile. Okay. So I have to, this is compressive. So I have to cumulative strength will be in compression as PUB comma X. That it will be 571. This is 571 kilometer. Okay. 571.8. This is tensile minus it will be 155.23 kilonewton. Okay. So the resultant will be 5 PUB comma X will be 416.6 kilonewton compression. So what we got, this is the strength of our column when there was uniaxial moment as well. For example, if there would not have been a uniaxial moment, then this reduction would not have taken place, 155. So the strength would have been on a higher side. So we can relate from this that uniaxial moments or later biaxial moments, you can also see that these reduce the compressive strength of the column. PUB to 4 over 16.6 kilonewton. So we have to, for this column, we have to check in flexure as well. Design strength component flexure. That's the fifth and the last point. Design strength and flexure. That is P, sorry. F flexure as MUB along X. Okay. MUB will be similarly contribution from the concrete. MC plus contribution from the steel, ms. Okay, mc plus ms, and mc will be cc into liver arm. Okay, cc into liver arm. I already wrote the formula as cc was 517. Okay, 57177 times 0.5 d is 500. Okay, minus 0.416 xu. 0.416 xu is 210.6. Okay, this comes out to be 92.85 into 10 power 6 Newton mm. Okay, MC. And for MS, we have to take the summation of all the rows. MS comes out to be summation CST times YI. YI is the liver arm for ith row. Okay. When we take this summation as corresponding to EH CST times YI, we have to take this for the first row. C was 360.9. You can back check all the calculations. 360.9 multiplied by minus 189.5. I already calculated it. Second row, you already know that there was CST as 131 megapascal, but for it YI is 0. Okay. For last row, it is 345 minus 0.447. FCK 25 is FCK times its YI is positive 189.5. Okay. Okay. Each is multiplied by 982. Okay. We get MSS 129.3 into 10 power 6 Newton mm. Okay, so MUBX design structure component of our column in flexure when it is subjected to axial load and uniaxial eccentricity is 92.85 plus 129.3 and unit conversion 10 power 6 Newton mm is kilonewton meter. This will be kilonewton meter. So MUBX will be 222.15 kilonewton meter. Okay, this our PUBX comes out to be 416.6 kilonewton, and this comes out to be 229. From this, I will give star point here as well. From these two values, you can now calculate that what was the eccentricity of the loading that is acting on our column. So our eccentricity EB along x direction, it's only uniaxial eccentricity. It is moment MUBX divided by the axial load. PUB Newton meter divided by 416.6, 416.6 kilonewton. Everything is confirmed, so I will get a 533 point. Okay, this is the loading eccentricity, uniaxial eccentricity acting. Sorry, EB comma X is 533.2 mm. Okay, so this completes our analysis problem whole. We calculated design strength component in axial compression PUBX, and we calculated design strength component in flexure MUBX, and also corresponding eccentricity uniaxial eccentricity. This was all for today. Thank you everyone for joining this section.
Thank
You
you.
may leave.